In this video, it's a continuation of section 3.2, simplifying and applying properties of rational exponents, but more specifically, your learning target will be to simplify higher order radicals, actually using that radical notation. So I'm going to go through a bunch of examples and just show you how to simplify a few things, and some of it's going to be similar to what we've done in the past, and I'm going to try to build on some of the things we've looked at in previous chapters in order to kind of use that to springboard into this new lesson. So the first example I'd like to show you is the cube root of 24, and I need to simplify that. Now, just like if it was a square root, we want to break down the number, and instead of looking for a pair of the same number, we're actually going to be looking for triples of the same number because of that index. Because it's a cube root, we want to look for perfect cubes inside of the radicand. So what I'm going to do then is break this down. I know 24 is the same as 12 times a 2, and I'm stuck with that 2, but I can break 12 into 2 times a 6. I'm stuck with that 2. And I can break down 6 into a 2 times a 3, and I finally have reached a dead end. So what I'm going to do now is rewrite this as the cubed root of, I have really 1, 2, 3 2's, right? 1, 2, 3 2's being multiplied, along with a 3 to make 24. Now, because this is, again, a cube root, this is a great thing because I have 3 2's inside of my radicand. That means those guys can leave and exit as 1 in the front. So I can pull a 2 out, and I'm still left with a cube root of a 3 inside. Now, since there's only one factor of 3, that guy's stuck in there and I'm done. Now, just to kind of note, one other way I could have written this, because it will come into play later and I think make your life easier, instead of writing that as 2 times 2 times 2, I think you would agree, I could have written that as 2 to the third times a 3. And then you could just realize, like, hey, I have a 2 to the power 3. There's my perfect cube. I can pull out 1, 2, and be left with the cube root of 3. Either way, you're fine. Let's look at another example. Let me do the fourth root of 64. Once again, I'm going to see if I can break down 64 into any perfect power of 4. So 64 I know is 8 times an 8. And I know 8 can be broken into actually 3 2's, right? Each of those 8's have 3 2's in them. I know that much. And so all in all, I have a total of 1, 2, 3, 4, 5, 6. Now I could write that as 2 to the 6th, right? But I don't want perfect 6th powers. I want perfect powers of 4. So instead of writing 2 to the 6th, I'm going to write 2 to the 4th times 2 squared. Now I think you'll agree, all in all, I still have 6 2's inside for my radicand, but I did that in a clever way so that I can recognize, hey, here's a perfect power of 4 that matches my index, and I can pull a 2 out there, and I have still a fourth root of 2 squared inside. Now, of course, I wouldn't want to leave it as 2 squared. I know 2 squared is the number 4, so the best way of writing this would probably be a 2, then a fourth root of 4. And I am finished. There are no more perfect powers of 4 inside of that radical. Let's look at another couple of examples. So let's move on to something a little bit more fun. Let's say I had 5 times the fourth root of 64, x to the 6th, y to the 4th. Alright, this is kind of a fun one because my index is 4. That means I'm looking for all perfect powers of 4 inside of my radicand. Now this 5 is just a coefficient. I'm stuck with that 5 in front. And what I'm going to try to do is break down that 64 into powers of 4. And I think, based on the previous example, if you remember, I'm going to rewrite that as 2 to the 4th times a 2 squared, right? Remember 64 was really 2 to the 6th. So I'm going to break it down in that fashion so I can see here's my perfect power of 4. And now instead of x to the 6th, I'm going to do the same thing I did in the previous example. And instead of writing it as a power of 6, I'm going to split those x's up into an x to the 4th times an x squared. There's still a grand total of 6 x's all being multiplied together, but this guy now is a perfect power of 4. And the y to the 4th already is a perfect power of 4. So that means I'm allowed to take out of this thing a 2, an x, and a y. So I have a 5 in front already, and if I pull out a 2, an x, and a y, that'll be what's in front, and I still have the 4th root of this 2 squared is left over, that's really the number 4, and this x squared is left inside. Now if I can, I'm going to multiply stuff together in the front. 5 times 2 is 10, and then I have an x, y, and then the 4th root of 4x squared. Please don't forget your index. I know a lot of students make the mistake on a quiz or a test. They just write a square root sign instead of really a 4th root. That index won't change throughout the problem. Let's take a look at another one. Just so you get the hang of it. This one will be a 3/4 root of 324 x to the 5th and y squared. So I'm now looking still for those perfect 4th powers, right? So 324 I don't really recognize. Let's see if I can break that down. I know that's going to be 2 times, let's see, 324 cut in half is 162. 162 if I divide by 2 is 81. And right there, I know 81, I recognize as 3 to the 4th. So I'm going to stop there. So if I rewrite this, I have a 3, and then I have a 4th root of 3 to the 4th. And don't forget, I multiplied a 2 and a 2, so I'm going to write that times 4. 2 times this 2 times this 2 is my 4. And instead of writing the x to the 5th, I'm going to write it as x to the 4th times an extra x. I still have 5 x's in there, and then I have a y squared. So I have a 3 to the 4th is a perfect power of 4 and an x to the 4th, but nothing else is a power of 4. I'm stuck with a 4xy squared inside. So I'm going to pull out a 3 to join this 3, so I have a 3 times a 3 in the front, and I also get to pull out an x, and then I have 4th root of 4xy squared. I would simplify that by writing 9 instead of 3 times 3, 9x, and then 4th root of 4xy squared. I'd like to show you a few more examples that are going to be a little bit more sophisticated. Let's look into multiplying radicals. So let's multiply. And this relies on some of the same things we've already done before. They just look a little bit scarier because of the indices are a little bit higher on the radicals. Let's look at this one. Let's say we have the cube root of 4x to the 4th times 2 times the cube root of negative 3x to the 4th. So a couple of things that you may want to realize. When you have a radical, okay, like I have a radical here, and I have a radical here. Any numbers that are in the front, these are coefficients, right? Now, if possible, I would multiply the coefficients to each other, but in front here, there's really only a 1, and 1 times 2 is a 2. So I'm going to write that 2 out in front, and now I'm going to multiply these two cube roots together. Now, notice, since they're both cube roots, I can multiply the insides together. What I'm really using is the following property. If I have the nth root of A times the nth root of B, as long as they're both nth roots, I'm allowed to bring A times B together. I can do the nth root of A times B all together. So I'm going to rewrite this as the cube root of, I'm going to multiply 4x to the fourth times negative 3x to the fourth all together. So that's going to be 2 cube root of 4 times negative 3 is negative 12, and then x to the fourth is x to the eighth. Now I just have to do the same thing I was doing in the previous problems, right? I got to look for perfect cubes. Now 12, I don't know if I'm in good shape with the 12. And by the way, this negative is annoying. I'm going to show you a trick with this negative. That negative sign, think of as really a negative 1 times a positive 12. Okay? And realize this. If I take negative 1 and cube it, I think you'd agree you're still going to get negative 1. So what that means is I can pull out, in a second, I'm going to rewrite this as the cube root of all this. I'm going to pull out that negative 1. It is a perfect cube of negative 1. So I'm going to pull out a negative, so it'll become negative 2 cube root of 12. Now 12 I can't break down into anything besides a 2 times a 2 times a 3. There is no perfect cube there. So I'm stuck with the 12 inside. But x to the eighth, I'm going to show you a little trick. I could write it as x cubed times x cubed times x squared, so I can see my perfect cubes there, and I still have 1, 2, 3, 4, 5, 6, 7, 8 x's all together. But I'm going to write it as x to the sixth times an x squared. And the reason is this, guys. This is something I can take out. Really what I'm going to do is divide the exponent 6 by the index 3, and I'm going to pull out an x squared. So I have negative 2x squared, and I'm left with cube root of the 12x squared inside. The 12 and the x squared stay. The reason why I did that, guys, think of it this way. I have an x cubed that I could pull out an x, and I had another x cubed that I could have pulled out another x, meaning x squared, right? I really pulled out two x's there. But as long as I can write the exponent as a multiple of the index, I will be able to divide that exponent by the index to get the exponent that I'm going to have on the outside. So at the end of the day, it's negative 2x squared cube root of 12x squared. And I do realize that's a little bit tricky, so we'll take a look at another one or two. Check this one out. Let's go into some division. Now I'm going to start off with something a little bit more simple. You guys will remember if I did cube root of 3 over cube root of 8, what you'd like to do is see if you can just simplify right away anything. So cube root of 3 I know I'm stuck with, cube root of 3, but 8, that's 2 to the third. The cube root of 8 is simply 2, and it's simplified. This is my answer. And the thing you have to keep in mind, that there can be no radical in the denominator. So in this case, geez, I can't get messy in a hurry here. The denominator. We can't have any radicals left in the denominator. So in this case, that's simplified nicely, and I only had 2 in the denominator, so I didn't have to worry about that. Let's call that example 1 for the division. Let me do another one where it doesn't turn out quite as nice. Let's say I had the cube root of 2 over 3 cube roots of 3. Okay. Unfortunately here, guys, I can't simplify the numerator. The cube root of 2 is already simplified. There's nothing to pull out there. Cube root of 3, I can't pull anything out there. There's only one factor of 3, so I'm stuck with that. But I do not like this cube root of 3 here. I need to get rid of it and rationalize the denominator. Now you might remember what you would do is just simply multiply top and bottom by the square root you see in the bottom. And this is what I see a lot of students do. There's a couple problems. First of all, this is a square root, right? And this one is a cube root. They're not even like roots, so it's going to have to be a cube root. Now, this is a little bit better if you change them to cube roots. However, there's still an issue here. And I'm going to kind of point it out right now. If I were to, oops, let me undo that. If I were to multiply these together as they were, would you agree I would have the cube root of just a 3 times a 3? There's only really 2 3's inside of that cube root. I don't need 2 3's. I need to have 3 3's, right? In order for me to be able to pull out a perfect cube of that 3. So it'd have to be a total of 3 3's because it's got to be a perfect cube. So in order to make it 3 3's, well, what if we did this? What if we did a 3 squared inside? Now when I multiply these together, I will have 3 3's all being multiplied together. So let me show you what this turns into. In the top, let me just rewrite it. I don't want to do too much. I'm going to do the cube root of 2 times the cube root of 3 squared, which is 9. I'm going to write it like that. In the denominator, I have this 3 in the front times the cube root of 3 cubed. And this is what you want to see because the cube root of 3 cubed is the number 3. So the denominator is 3 times this 3. The bottom number is 9 now. And in the top, because these are like radicals, the cube root of 2 times the cube root of 9, that's the cube root of 2 times 9, or 18. Now don't be silly and think you can divide 18 and 9. 18's inside of the cube root, 9 is not. Hands off. You're done. Cube root of 18 over 9 is your final simplified answer. Let me show you one more of division that's more fun. Let's take a look at this. If I had 2/4 root 12x squared y to the 4th over the 4th root of 27x squared y to the 4th. Now, this one looks super duper scary, but it's not, and I'm going to tell you why. Look at these radicals. Do you see how they're both the same index of 4? If they are, and hopefully you said yes, if they are, if you have like the nth root of a over the nth root of b, you can do the nth root of that fraction a over b and put the inside, the radicand, in just one fraction. So this is what I mean. This 2 is out in front. I'm going to keep that 2 there, but I'm going to make it times the 4th root of this entire fraction where the numerator is the 12 x squared y to the 4th, and the bottom is a 27 x squared y to the 4th. Now that's beautiful because x squareds cancel, y to the 4ths cancel, and I think 12 over 27 will, I think there's a, let's see, that fraction is really 3 times 4 here, and 27 is 3 times 3 times 3. I can cancel one of the 3's out. So it's really the same as 4 over 9 if I reduce that fraction. So I have 2, and then I have the 4th root of 4 over 9. So that's simplified pretty nicely. The only problem here, guys, you have to realize is that I have 2, and I have the 4th root of 4 in the numerator, and I really have the 4th root of 9 in the denominator if I, split that fraction up. So I have to rationalize here. Now realize this, 9 has a 3 and a 3 in it. How many more 3's do I need to make it a perfect 4th power? Well, hopefully you're saying another 2 3's. So in order to rationalize this one, I have to multiply the top and the bottom by another 3 squared inside of the radical. So both top and bottom are going to get the 4th root of 3 squared. In this case, what I'm going to end up with in the top is a 2 and the 4th root of, if I multiply 4 times 3 squared, That's really 4 times 9. That's 36. And in the bottom, I end up with the fourth root of 3 to the power 4, which is just the number 3. So I have 2 fourth root 36 over 3, and it is simplified. Thanks for watching. I'm going to have another video for showing you how to add like radicals in a moment.